Okay, so here I'm going to be going over the FRQs that were in the progress checks. So I'm going to be going through these rather quickly and just referencing the scoring guideline to talk about things to look out for, and also to provide a little bit more detail in terms of how to approach the problems and how to think about the problems, not just what the final solution ends up being. If you have any questions on any part of any of the FRQs, or you want to follow up on one of them just because it seems you're having difficulty understanding how to approach the problem or these types of problems, I will be available after school during Pride Block, and I can help you prepare so that we do very well in the tests on Friday. So I'm going to go over these rather quickly. It's fairly late. I started recording and then a part of it messed up. So I already have some of the writing here. Let's just get right to it. So FRQ number 1, here we have a cart moving along a straight track. The cart's position x is initially at 0, and the velocity v is a function of time described by the quantity bt squared minus tct, where b and c are positive constants. The cart's instantaneously at rest at time t equals tr, as shown in the figure. On the axis, sketch a graph of the cart's acceleration as a function of time for the time interval shown. All right. So here, what we need to do is basically we need to know that the slope of the velocity time graph is the acceleration, right? By definition. To be more specific, using calculus, the slope of the graph, that's basically taking the derivative, right? If you're doing slope of the tangent line, that's how it's defined. So basically, I'm looking at this function here, and I'm graphing what the slope of that function is with respect to time. So if you notice here, it starts off at 0 initial velocity, and that velocity starts to decrease. It's downward sloping for the first part of the graph. Then it reaches a point where the slope is 0. So that's like the minima of this little parabola that's shown, and that's about halfway through the motion, right, in terms of time. Then at time tr, that's when it's transitioning from negative velocity to positive velocity. So at time tr, the velocity is 0, and then the velocity continues to increase. So basically here, I have some function in terms of t squared. When I take the derivative of that function, I'm just going to have a function, with respect to t. I'm basically going to have a line. You take the derivative of a quadratic, you end up with a linear function. So that's what I do here for part B. We have here bt squared minus ct. I take the integral. Now you can take so there's a part here, right? So from here to here. Notice I just set up like the indefinite integral for like the definition of velocity. In the third line here, I actually give the bounds of integration. So technically we're integrating from t equals 0 all the way to t r. All right, and we're trying to figure out what the initial position is in terms of tr, right, or at time tr. Now notice something else that comes up. So it says for parts B and C, express your answer in terms of B, C, and physical constants as appropriate. All right, so what we're going to do is we're going to integrate the function, then we're going to evaluate the function to express it in terms of just B, C, and physical constants. So here on this line, right, so now on this line here, we have that I'm just doing the actual integral of the function. And as a reminder, how to take an integral, you have the power rule for integrals, where if I have some function, cx to the n, right, so this is integrating simple polynomials, right, so it's not too bad. All you need to do is you need to increase the exponent by 1, right, so integral of cx to the n is x to the n plus 1, and then that coefficient, you have to divide it by n plus 1, right? So it's c over n plus 1 times x to the n plus 1. A simple example, if you're integrating 2x squared, you'd have to increase the exponent by 1, so it's going to be x cubed, and then you divide the coefficient by n plus 1, so it'd be 2 over 3, right, x cubed, right? That's the integral of 2x squared is 2 over 3x cubed. Now let's actually do it for this function. So I have bt squared minus ct. I'm going to evaluate it one at a time, right? So here I have bt squared. That's going to come out to b over 3 times t cubed. And then I have the minus ct here. and that becomes minus c over 2 times t squared. All right, and then I have to use the bounds of integration. So for this particular problem, it turns out to not be a big deal. But just generally speaking, when you're evaluating an integral, especially a definite integral, you have to typically just put in these little brackets, and you are going to take this function, right? So t, I'm going to sub in tr, right, which is just another variable, and then evaluate it. And then from the upper bound of integration, I'm going to subtract the lower bound of integration. So notice we start at time t equals 0, right? So if I plug in a 0 here into the function, then I just end up with 0. So I just end up with b over 3 times tr cubed minus c over 2 times tr squared. And I throw in this plus x naught here, right? So technically, whenever you take an integral, you have to add this like constant of integration, right? So this is the constant of integration. And the reason you have to do that, technically, is because integration, basically that's the opposite of taking a derivative, right? So the process of finding an integral of a function, you're taking the antiderivative. And if you notice, the derivative of a constant number, right? So if I have a constant value, right, that doesn't have any time associated with it, right? It's just a constant value. Then the derivative of that ends up being 0, right? So velocity is a derivative of position. Basically what it is, the constant of integration when dealing with kinematics and dealing with physics, for well, specifically kinematics, that constant of integration is the initial position, right? So the initial position doesn't vary based on time. It just says a constant value. So if I had some position function and there was this initial position that was not 0, if I were to take the derivative of that function, I would get a velocity function, and that initial position, right? If I take the derivative of the initial position with respect to time, well, there's no, time component tied to it, right? So it just turns out to be 0, right? So the derivative of a constant value ends up being 0. So here I have my expression for the position at time tr, and I need to evaluate it in terms of b, c, and physical constants, right? So I need to figure out what tr is in terms of b, c, and physical constant. Well, one important piece of information is that we know that the velocity is 0 at time tr, right? So what I can do is I can set the velocity function equal to 0 at time tr. So my velocity at time tr is equal to 0, because that's what it shows on the graph, right? The velocity is 0 at that point. So I'm just going to set this equal to the actual function. So my function is bt squared minus ct. And then when I solve for t, right, I can factor out a t. So I have t times bt minus c. I'm setting that equals 0. So I can divide both sides by t, and I just end up with bt minus c equals 0. And then you do the algebra steps, you end up with t is equal to c over b. So now I'm going to plug this in to this function here, right? So I'm going to now plug this in to here, all right? So let's evaluate that. So my position at time tr is equal to b over 3 times c over b. Hold on, let me turn off the... Oh, wait, no. Let's just do it like spell check. Quantity squared minus c times c over b. All right. And then my final expression is going to come out to... one second. I was looking at the... Oh, yep. You got to be careful. All right. I almost made a mistake. The position function, it's c over b cubed. For a minute there, I was looking at the velocity function. And then this here is going to be squared. Okay. No, and this is c over 2. It is very late at night. I am going to try to make less errors. Okay. So again, here's my position function. B over 3 tr cubed minus c over 2 times tr squared. And I just plug in my value for time into the function, and now let's evaluate it. So c over b, quantity cubed. I have a b over 3 here. So b over 3 times c cubed over b cubed. That just comes out to 1 over 3 times c cubed over b squared. All right. Then we need to evaluate this one. So I have c squared over b squared times c over 2. So I'm going to end up with 1 over 2 times c cubed over b squared. And if you notice here, these have common denominators, right? So all I need to do is I need to, or I should say, there's a c cubed over b squared term, right, in each one. So I just need to get common denominators here so I can actually subtract the fractions. Here my common denominator is going to be 6. All right, so it's 2 over 6 times c cubed over, actually I'm just going to factor that out. I'm just going to factor out the, so 2 over 6 minus 3 over 6 times c cubed over b squared. All right, so now I'm evaluating this. Whoops, let me put this here. All right, so here I'm going to get negative 1 over 6. So negative 1 over 6 times c cubed over b squared. All right, let me make that more obviously a 6. All right, and that's going to be our answer. All right, and now for part C. Also, keep in mind, like, definitely look at the scoring guidelines, right? So, for example, for the first one where we drew the acceleration time graph, we knew that it starts off negative and it becomes positive, and that about halfway from t equals 0 to t equals tr, that's when the acceleration is 0. But notice here on the scoring guidelines, they're actually not super sticklers about that particular fact, right? So as long as at time t, as long as a time significantly greater than t equals 0 and significantly less than t equals tr, that the acceleration crosses the horizontal axis, okay? So it doesn't have to be exactly halfway, even though it certainly looks as if it has to be halfway, right? Because that's where the minima is. That's when the slope is 0, is about halfway between t equals 0 to tr. That's not a big deal when it comes to the points, right? So looking at the scoring guideline, I think is a very good idea because that's how the test is going to be graded. So you kind of get a feel for how the actual AP FRQs are going to be graded as well. And then here we see the scoring guidelines for part B. So we have a multi-step derivation, right? We took the integral. We got a point for the correct expression, a point for indicating that the position is minimum when the velocity is 0, right? That's what we did here. And then for the correct solution, when velocity is 0 at time, not at v naught, but like at some later time, right? T equals tr. And then substitution of derived time into derived position equation with no symbolic quantities other than b, c, and physical constants. Yeah, so this is something interesting. This is something that's important to note. So if you wrote like this expression here on the third, or here, this one here, the b over 3 tr cubed minus c over 2 tr squared, that's actually not enough to get the points because you have to express it in terms of just b and c and fundamental physical constants, right? So that's why we had to solve for time t equals tr, solve for that in terms of b and c. All right, so now let's look at the very last part. So we got to derive an expression for velocity when it passes through position x equals 0 at a later time t greater than 0. So let's write down our velocity function. So our velocity function with respect to time is equal to bt squared minus ct. And then we know that at x equals 0, so at x equals 0, we have the position function. We're going to set it equal to 0, right? So b over 3 t cubed minus c over 2 t squared, that has to equal 0. All right, so if we solve for t, I'm going to factor out a t squared from this whole expression, right? So b over 3t minus c over 2, that's equals 0. Divide both sides by t squared. Obviously, 0 divided by t squared is just 0. So b over 3 times t minus c over 2 equals 0. I'll move that over to the other side. I'm just going to do every step just to be thorough. Okay, is equal to c over 2. And then solving for t, I get, basically I'm going to multiply both sides by 3 over 6. Right, so I have here 3. Oh, wait, what am I doing? It's b over 3. I'm mixing up my b's with 6's. Okay, b. Okay, b over 3. All right, so I'll multiply both sides by 3, divide both sides by b, so I can get a final expression, 3c over 2b. That's my time. And I'm going to plug this time in to the velocity equation. Okay, so now my velocity, this is basically my velocity when x equals 0, right? So my velocity when x equals 0 is equal to b times t squared, which in this case is 3c over 2b, quantity squared, minus c times t, which again is 3c over 2b, all right? So now when we do the math, what we should end up with is, so 3c squared over 3c over 2b quantity squared, I end up with 9c squared over 4b squared, right? So I have 9c squared over 4b squared times b, right? So b times 9c squared over 4b squared. And then I have here for this term, I have minus 3c squared over 2b. All right, so one of these b's cancel out. All right, so here on this term, the b cancels out with the b squared. Right, and writing it out again, I have 9c squared over 4b minus 3c squared over 2b. So we need to have two common denominators. All right, so my common denominator is going to have to be 4b. All right, so I'm going to multiply this fraction here, the 3c squared over 2b. I'm just going to multiply by 2 over 2. All right, so it's the same thing as 9 over 4 minus 6 over 4. Now it's a 6, not a b. And then all that times the c squared over b. All right, so I'm making sure that I have common denominators. 9 over 4 minus 6 over 4 is just 3 over 4. So we have this equal to 3 over 4 times c squared over b. And that's my final answer. All right, so that's the expression. For velocity, let's look at scoring guideline. Yeah, and that's all you have to write down. All right, so that's it for the first one. Not too bad. I'm looking at the... All right, let's look at FRQ number 2. Okay, so let me add some space here. Did the long press it? All right, whatever. I'm just going to do that. Okay, good. I'm just trying to create a new page. All right, so here we have a car that is driving along a straight line and starts from rest at t equals 0. The car moves acceleration a. That varies with time t according to the equation a equals p over p minus qt, where p and q are positive constants. Okay, so here we have to represent the car in two instants of time. At t1 equals p over 2q, and t2 equals 3p over 2q. On each dot, draw an arrow represent direction, if any, of the car's acceleration at the time. If the acceleration is 0 at either time, write a equals 0 next to the appropriate dot. All right, so at time t is equal to p over 2q, I'm going to plug it into the acceleration function and see what the value is. And notice it says that p and q are positive constants. So let's actually go through that. So I have a as a function of time is equal to p minus qt. All right, and let's evaluate it when t is equal to p over 2q. So when t is equal to p over 2q, I have the acceleration equal to p minus q times, well, p over 2q. All right, and when I evaluate that, the q's cancel out, right? So q times p over 2q, I just end up with p over 2, so p minus p over 2, and that just comes out to p over 2. All right, so that's my acceleration, and because p is a positive constant, I know I have a positive acceleration. So I'm just going to draw that as going to the right. All right, so on the dot, I'm drawing that the acceleration is going to the right. Now at time t equals 3p over q, or I'm sorry, 3p over 2q, you're going to do the exact same thing. All right, so 3p, oh wait, whoops, let me write that up. All right, so the acceleration is equal to p minus q times 3p over 2q. All right, and then we're going to end up with negative p over 2, right? So here I have p minus 3 over 2 times p, okay? So basically I have 2 over 2p minus 3 over 2p. All right, and that's going to come out to negative p over 2, right? So in this case, the acceleration is going to be negative. All right, now let's look at the velocity. Okay, wait, hold on a second. So dot 3 represents a car at the same two instances in time. On each dot, draw an arrow. Okay. Oh, okay. That's just saying you have to now draw it for the velocities, right? So in order to do that, I have to get the velocity function, right? So I know that the velocity function is going to be the integral of the acceleration function. So I have to integrate again, and I'm going to use the chain rule, or not the chain rule, what am I saying? I'm going to use the power rule in order to take the integral of this polynomial, right? So my velocity with respect to time, so v sub t is equal to the integral of a sub t. I'm just going to keep it indefinite. So here we have this equal to, let me move something. All right. So here we have this equal to the integral of p minus qt. All right. And then using the power rule, the integral of p, all right, let me add my little dt there. All right. So we're doing this with respect to time. I'm going to add my little dt. Okay. So integral of a constant, right? So if I had just some constant value, the integral of p is just going to be pt, right? So again, using the power rule, let me do a simple example just because this is new for a lot of us, right? So let's say I want to take the integral of the number 5, okay? So another way to represent that is the integral of 5 times t to the 0, right? And remember the power rule, you have to increase the exponent by 1, and then you divide the coefficient by that by n plus 1. So basically n is 0, right? So I'm going to do 5 divided by 1 plus 0, which is just 1, and then times t to the 0 plus 1, which is t to the 1. That's basically just 5t, okay? So the integral of 5 is 5t. And similarly, the integral of p is going to be equal to p times t. And then the integral of qt, well, it's going to come out to minus q over 2 times t squared. All right. And if I want, I can evaluate it and see if it's going to be positive for both times, right? So that's what I ended up doing. Okay, so it's getting late. So in the interest of time, I'm going to be skipping a little bit of steps. All right, so when I evaluated the integral, so when t is equal to, right, so the first one's going to be p over 2q. So p over 2q, I have that the velocity would equal p times p over 2q minus q over 2 times p over 2q quantity squared. All right, and if you do the algebra, just take my word for it. This is going to come out to 3p squared over 8q. All right, I'm going to have to start skipping some steps because it's getting late. All right, try it out yourself. You should get 3p over 8q. These are positive constants, so I know that the velocity has to be positive at that point. Okay, and then here at time t equals 3p over 2q. All right, I'm going to do the same exact thing. So velocity is going to be p times t, which in this case is 3p over 2q minus q over 2 times, well, p over 2q. Oh, whoops, what am I saying? 3p over 2q. We're looking at time 3p over 2q. All right, and again, just work through the algebra. Take my word for it. This actually also comes out to 3p squared over 8q. All right, so that's the velocity. All right, so the acceleration, going back to acceleration, it starts positive, it becomes negative, but the velocity is going to be positive at both times. So now part B, we have to derive an expression for the cart's velocity as a function of time using p, q, and t and other physical constants. Well, we just did that, right? So we did that to determine the velocity as a function of time. Another way to think about it, actually this didn't give us a graph. Let's see here. All right. Well, anyways, we already evaluated it, so that's the work shown for it. So we know that the velocity with respect to time is equal to pt minus q over 2 times t squared. All right. For part 2 of part B, derive an expression for car's maximum speed within the time range. T is greater than or equal to 0, and t is less than or equal to 3p over 2q. So something to know about this, my max velocity, right? So as we can tell from this function, I start with some initial positive velocity, and then my velocity is going to be decreasing over time, right? As soon as my velocity, I'm sorry, I misspoke, not my velocity, my acceleration. So I'm going to start with some positive acceleration. My acceleration will decrease with respect to time, and at some point, my acceleration is going to be 0. And then my acceleration is going to be negative. And once my acceleration is negative, I'm going to start slowing down. So the key fact to know is that I'm going to have max velocity when acceleration is 0. And that's true for this function. So for this acceleration function, once it's equal to 0, that's when I'm going to start to decelerate. All right, I'm going to start slowing down. So I'm going to reach my max velocity at the end of all of the positive acceleration. All right, so I just need to evaluate it. So I know that A is equal to P minus QT. I'm sorry, QT. So P minus QT. I don't know why I want to keep putting Q over T. QT. All right, I'm going to set that equals 0. T is equal to P over Q. All right, now I'm going to plug that P over Q into the expression for velocity. And I'm just going to have to go kind of fast because it is getting late. P over Q. All right, minus Q over 2 times P over Q quantity squared. And that's going to equal P squared over Q minus P squared over 2Q. All right, and then you're going to simplify, and you get P squared over 2Q, right? Just kind of like 1 minus a half, right? If I factor out the P squared over Q, 1 minus a half is a half, all right? And that's why I get P squared over 2Q. All right, that's my expression. Now part C, so we need to, whoops, I keep messing that up. All right, part C, now we have to actually graph this, describe, why it's not consistent with the following, the equation. All right, so here I am graphing. Oh, wait, I kind of skipped some. All right, let's look at part C. So on the same road that the car moves along, a bicycle is moving at a constant velocity in the positive direction. Okay? On the axes below, sketch a graph of the car's velocity as a function of time during the time interval indicated on the axes. Clearly label the graph car. And on the same axis, sketch a graph of the car's velocity as observed in the reference frame of the bicycle. Clearly label the graph bicycle frame. All right, so we are looking at our velocity as a function of time. I know that my velocity at time p over q is equal to p squared over 2q. All right, and so let's actually express that on the graph here. So at p over q is when my velocity is going to be at the maximum. Also, I know that the function for the acceleration is linear, right? So it's a continuous linear function. Therefore, the acceleration, all right, should be symmetric. So if I start at some positive acceleration, the acceleration is 0 at p over q, and then it's going to become negative, right? So at p over q, the acceleration becomes, it transitions from going from positive to negative, right? Because the acceleration is 0 at point p over q. And then at point 2p over q, the velocity is going to be negative, but have the same initial value, right? So you can just evaluate it, right? So we're just going to plug it in to the equations to actually get the values. So let's see here. Oh, you can just plug it into the function, right? So the velocity at time t equals 0, I have this function pt minus q over 2 t squared, right? T equals 0, velocity 0. At p over q, we know the velocity is going to be p squared over 2q. At 2 times p over q, if you evaluate it, you get a velocity of 0, and then it's going to just keep going down, right? Yeah, so that's pretty much it. So let's just look at the graph on the scoring guideline. So in terms of drawing the bicycle graph, all it says is you're looking at the observed reference frame from the bicycle. So the bicycle is traveling in the same direction as the car. If say the bicycle is traveling at, I don't know, 5 meters per second with respect to the road, and the car is traveling at 50 meters per second with respect to the road, from the perspective of the bicycle, it's going to look as if the relative velocity is 45, right? So from that example, we understand with how relative velocity additions work, if the bicycle is moving in the same direction as the car, is going to appear as if the car is moving more slowly with respect to the bicycle, right? Because the bicycle is also moving, all right? And just to really drive the point home, let's say somehow, I don't know, we got Lance Armstrong on the bicycle and he's going super fast and the car is like really slow. So they're going at the same speed. If two cars, or bicycle and the car, if they're going at the same speed, the relative velocity between them is going to be 0 because they're going at the same speed. So that's kind of giving you an intuition for how the relative velocity works. What this bicycle, what the cyclist is going to observe from his reference frame is that the car seems to be traveling more slowly, right? And it's not that it seems, like all velocity and positions and acceleration, they're measured with respect to some reference frame. And there's no preferred reference frame. The cyclist reference frame is just as valid as the reference frame from someone standing on the side of the road. But the point I'm trying to get across is that it's going to appear as if the car is traveling more slowly for someone on the bicycle traveling in the same direction as a car versus someone who's just standing there on the side of the road. So in other words, it's shifting the velocity down. If I draw the velocity of the car as observed by the cyclist, right? So relative to the cyclist, it's going to be shifted down, right? By how much? Well, by the velocity of the cyclist, right? So that just is shown in the scoring guideline. You see here, this is the car's frame. And here in the scoring guideline, they tell you what they're looking for. But as we were saying, it starts at 0 for the car. It goes up to some max value. And then at time t equals 2p over q, if you evaluate the function, you see the velocity 0. And it's just going to be, if the acceleration, if you look at the function for velocity, right, we have pt minus q over 2 times t squared. That is a quadratic, right? It's going to be in the shape of a parabola, and it's going to be concave down, right? Because the coefficient in front of t squared is negative, all right? And that kind of follows what we're seeing here. But its exact value on the different points, that's important, okay? You don't need to actually show the exact value for at time t equals 3p over q, but at time t equals 0, at time t equals 2p over q, the velocity better be 0 for the car's frame. And then at p over q, that's the relative maxima. And then notice how the bicycle frame looks exactly like the car frame, except it's just shifted downward. And that is because the cyclist is moving in the same direction as the car. So the relative velocity between them is smaller than it would be for an observer on the side of the road. All right, so now let's move on because it's getting late. All right, so FRQ. C. It's the graph. Okay, I'm not going to sketch the graph. All right, so FRQ number 3. So now we're on number 3. All right, now this one is the experiment one. Conveniently, we did a very similar experiment, right? So we didn't do horizontally launched projectile, but we did projectile motion in general. And we even had the little carbon copy paper on top of the target, and we were able to track and mark where the projectile landed. Now, for this experiment, they tell you 60 centimeters tall when it's mounted horizontally and move vertically to different heights. So you got a meter stick, we got several sheets of plain paper, several sheets of carbon paper, and it asks you on how to set up the experiment. So they give you a sample response in the scoring guidelines. Let me just kind of tell you what I would say, right? So what I wrote down, and I'm not going to write it down. I'm just going to just say it. All right, so I said we're going to measure the height from the floor to the bottom of the sphere, lay out several sheets of paper and carbon paper on top in order to record the position where the ball hits, right? So like the position of the ball when it hits the floor. We're then going to use the meter stick, right? So I'm talking about the measuring device we're using. So we're going to use the meter stick to measure the horizontal range of the projectile. Also mention you're using the meter stick to measure the height of the ball, right? So the initial height of the ball before it's launched horizontally. Repeat the measurements, okay, for varying heights of the launcher, right? So I said like from the range of close to 0 to 60 centimeters, right? So, I mean, if I have 60 centimeters of travel for the height of the sphere, I don't want to just I want to look over the whole range of the data. All right. Something that they put in the sample response, I don't think they mentioned doing like multiple measurements for the same data point, right? So they provide, well, that's for a different question. But basically something I noticed here, it says for part A, include steps necessary to reduce experimental uncertainty. So generally speaking, if you want to reduce experimental uncertainty for any observation, you're going to want to take multiple observations and perform statistics on that, right? So let's say you were to set it at, on the scoring guideline, they mentioned like 5 settings, right? So you set it at 60, 50, 40, 30, 20, 10, okay? Actually, that comes out to 6. But you know what I mean. So if you do it over the whole range of heights, for each height, you actually want to take a few trials, right? So you're going to want to do, I mean, at least 3, preferably 5. I mean, 10's kind of overkill. But the more data you gather for a particular trial, the more precise you're going to be, because any sort of measurement in the real world and real life is going to be, there's going to be some distribution to it. You're not going to get the exact same measurement each and every time. However, due to statistics, it is going to cluster around a mean value, and you can calculate the mean value by taking the average. All right, so I would recommend mentioning that in pretty much every procedure, and not just mentioning it. I recommend actually doing it when you're doing labs, okay? You don't want to just take like one data point for one setting and then just do like 5 data points in total. No, you gotta do repeated measurements, all right, in order to reduce that uncertainty. And then you can kind of see what the range of values are for a particular input value. All right, anyways, I got on long enough about that. It's one of those things we're just going to get better at as we practice, right? So as we do more labs, we write more procedures, we're just going to get better at it over time. So let's look at part B. Identify two quantities that when graphed, it will produce a straight line that can be used to determine V naught. All right, interesting. Now, this is actually very important as well, okay? So A, okay, so I spoke about the procedure. Okay, so just listen to the audio. All right, part B. All right, now we have to identify two quantities when graphed. It produces a straight line. Use to determine V naught. All right, this is pretty much how you're setting up every kind of lab question. Basically, when you are determining the value of some variable, all right, you're going to want to set it up. So the slope, you're going to set up your axes so that your data, right, so the independent variable and the dependent variable, the data that you actually gather, the independent variable you're going to want to put on the horizontal axis. The dependent variable is going to be on the vertical axis. And when you measure the slope of a line, you are measuring how the dependent variable depends on the independent variable, right? So as the independent variable changes, how does that affect the dependent variable? And then you get a general trend. And then if you set it up, if you set it up nice, then you can figure out whatever physical constant or whatever value you're interested in. You can figure it out by looking at the slope of the graph. All right. So if you have a function that's not linear, you have to do something called linearization. Okay, so you have to linearize. All right. So let me talk about what that means. So we have to actually solve for the experiment. We are determining, okay, how the range of the projectile is affected by the vertical height. So I'm going to go over this very quickly. So I know that V naught y is equal to 0. I have no initial velocity in the vertical direction because this projectile is launched horizontally. All right, so the equations I used, I know that the range, I just labeled it as x initially, and then I saw in a later part of the problem they used the variable d. I think that's going to be less confusing. So my range d is equal to my velocity in the x direction times time. All right, so my velocity in the x direction, which is basically just the launch velocity of the projectile launcher. It's a horizontal projectile launcher. Okay, so the velocity is, well, the horizontal velocity times time. All right, now I need an expression for time. So we know that this ball is going to be in free fall, and the initial velocity is 0. So I actually have a kind of a shortcut equation. I call it the free fall equation. So when your initial velocity is 0, you just know it's going to come out to square root of 2I over g. To derive it, I can write my vertical displacement equals v naught yt plus 1/2 at squared, where a is going to be negative 9.8. If v naught y is 0, that's 0. If I solve for t, well, my delta y, right, that's going to be negative, right? So I have it's falling, okay? So its y position is going to decrease. I have a negative vertical displacement. I divide that by 1/2 times 1.8, right? Or negative 9.8. And then that's how I solve for t, right? I take the square root of both sides. I end up with this expression. Now I'm going to plug this expression into the range equation. So I have d is equal to v times the square root of 2y over g. Now my dependent variable is the range. So range is dependent variable, right? The range depends on the vertical position of the launcher. The higher up the horizontal launcher is for a given velocity, the further the projectile is going to travel. Is dependent variable, all right? And the vertical position, the height, what am I saying? So the height's the independent, right? So we're changing the height, and and the range is going to depend. The range is going to depend on the height. Now I have to express this as a linear function. All right, so how do I do that? If I were to graph d as a function of height, okay, it's going to be a square root function. All right, and I can't perform a linear regression on that. But what you can do is you can change what you plot, right? So if I plot d, my height here, d in meters, and title your graphs, right? Range versus height. Okay, so as I change the height, so I'll just label this as h. Okay, so h is the height of the launcher. From our equations, that's going to be the y. All right, so instead of using h as our horizontal axis, what we actually want to do is I need to look at this equation, right? So I'm going to erase this for now. So I need to look at this equation, and I need to set it up in the form of y equals mx plus b. So I have d is equal to v times square root of 2y over g. All right, so what I could do is I need to kind of write this in the form of mx plus b. We're not going to worry about the y-intercept for now, but I know that I need to kind of rewrite this. So the height is the only thing. So these physical constants, like the g here for the square root of 2i over g, that needs to go into the part that is dealing with slope. So let me explain. I'm going to rewrite this. So d is equal to v times the square root. So v times the square root of 2 over g times h. So if I look here, oh wait, what am I talking about? Square root of h. All right. Okay, so if I look here, my vertical axis should be the distance. My slope is v times the square root of 2 over g. And then my independent variable is the height. So if I graph the range with respect to height, okay, so if I graph the range with respect to height, it's not going to be linear. But if I graph it with respect to the square root of height, okay, then I'm going to get a line. All right, so that's the basic idea. This. All right, so then the slope will equal v times the square root of 2 over g. I think they set it up different in the scoring guideline. I think they graphed d squared in the vertical. Yeah, they graphed d squared in the vertical and h on the horizontal. Regardless, you're going to get the same answer, right? Regardless of how you set it up. All right, so let's look at the scoring guidelines. No, it's for the different one. They did example response for part B. All right, graph involving launch height and horizontal distance traveled. Describing a valid method using a linear relationship to determine launch speed. There you go, done. The slope will equal the launch speed times square root of 2 over g. All right, now let's look at part 2. Actually, that was part 2. Part 1 was actually writing out the expression. So d is equal to v times the square root of 2y over g. All right, and then the slope's going to equal v times square root of 2 over g. So part D, we have a different lab. Let's see here. So here we have to identify all right, later students analyze their data, determine that V naught equals 4.1. Using the same launcher as part A, the students set up an experiment shown in figure 3. They disagree on the formula. One student says D is equal to V naught squared. over g times sine 2 theta L. Theta L being the angle of the launcher. All right. And student 2 says that he would expect D to be proportional to sine theta L, not sine 2 theta L. So unfortunately, student 2 does not know the Pythagorean identity, so that's okay. That's the part when you solve for projectile motion, you have a cosine theta times sine theta that equals 1/2 sine 2 theta. All right, well, that's pretty much it. But let's do it experimentally, right? So we know the Pythagorean Pythagorean identity, but you got to see if the data follows that. So this was actually pretty interesting. This idea of like experimentally determining whether or not this it's going to be sine 2 theta. But anyways, they have some data here. This is my different launch angles. I have my different ranges. And it says here, identify what quantities would be graphed to yield a straight line to be used to calculate an experimental value for n. All right, so then you just have to, again, go through the equation. So I have d is equal to v naught squared over g times the sine of n times theta L. All right, so what I'm going to do is I'm going to move this v naught squared over g to the other side. So I have d times g over v naught squared is equal to the sine of n times theta L. And then I'm going to take the inverse sine of both sides. So n times theta L is equal to the inverse sine of d times g over v naught squared. All right, let me double check. I got that. Yeah, and then what I'm going to graph here, so n is what we're experimentally determining. So I'm going to want that to be like the slope. All right, so let's set this up in terms of y equals mx plus b. So y is equal to m times x plus b. We're not going to worry about that. So here for my y, well, for my slope, I'm going to want n, okay? So my independent variable is theta launcher, right? So I'm changing the angle of launcher, and I'm seeing how that affects the range of the projectile. All right, the range of the projectile is my dependent variable. Now, to linearize this, your axes is not it's not going to be just d on the vertical axis. It's actually going to be the inverse sine of dg over v naught squared, right? So the inverse sine of d times g over v naught squared. All right, I'm running out of space here. And kind of the same thing. What do I use? Green, blue, yellow. All right. So green, this is my vertical axis. That's my dependent variable. My blue is the slope. So the slope of that line is going to be n. And then here, my independent variable is my launch angle. All right, so that's what I'm going to plot. All right, so you're going to plot sine, inverse sine of dg over v naught squared with versus theta L. Let's see here. What else are they going to ask for? All right, now this is where it gets kind of annoying. You have to actually plot the data, which means you actually perform the calculations. So here I have, 5 sets of data, 5 data points. So you're going to have to actually do the inverse sine of dg over v naught squared, where v naught is equal to 4.1. I'm just going to look at the scoring guidelines just to kind of show you what the graph could look like. This is an excellent graph. So yeah, they put arc sine. That's just a fancy way of saying inverse sine. It literally means the same thing. So arc sine of g times d over v naught squared, measured in degrees. All right, so always remember to label your units. All right, so these units are in degrees, and the slope of the line determines what the n value is. And notice that they created a data table calculating the arc sine of g d over v naught squared, and then they calculated for each of the data points the wait, what? Oh, I see. And the scoring guideline, you don't have to do it for both 10 and 9.8. It's just like, what if people use 9.8? If students use 9.8, they get a certain data set. If students use 10 for gravity, they get a different data set. That's all this is showing on the scoring guidelines. Yeah. And that's pretty much it. So you do the graph, you measure the slope, pick 2 points on the line that are easy to read, take the difference between those 2 points. Okay, that's your delta y over delta, or the change in the vertical over the change in the horizontal, which is what slope is, rise over run. And that's pretty much it. Wait, did I miss something? Part C. Part D, use a line draw to calculate an experimental value for n. Yeah, so basically, once you have the slope, or that's what you're doing. You're finding the slope. Slope is the experimental value for n. I think in the sample student response, they got about 2, right? Technically got 1.91. All right, but that's, within error. Okay, you're talking about it's like 5% error. So it's not too big of a deal. So yeah, n equals 2. That's basically it. All right, now finally for the last FRQ. All right, so here I have a position x as a function of time. Particle moves along x-axis, t equals 0. Particle's position is -3. At time t equals 1, t equals 3. Particle's position is x equals 0. All right, so using features of the graph, justify whether the particle's velocity and acceleration are either positive, negative, or 0 at time t equals 1 and time t equals 3. Your justification, okay. So here I have a quadratic, right? A downward-facing parabola. And we know that the slope of the tangent line is the derivative. The derivative position is velocity, right? Slope of position time graph is equaling to velocity. We all know that. So here I know that at t equals 1, right? So this is number 4. All right, let me change back to white. So at t equals 1, the slope of xt is positive. All right, at t equals 1. Also, I know that the acceleration is negative. And there's 2 ways you can explain this. So you could say that the slope of the graph is decreasing over time, right? So you're basically taking the second derivative. So I'm looking at the slope of the position time graph. I know it starts off as positive, it reaches 0, and then it becomes negative. Well, if your velocity is changing from positive to 0 to negative, that means you have a negative acceleration, right? My velocity is decreasing. So that's why it's negative acceleration at t equals 1. But that's also true at t equals 3, right? The acceleration is still going to be negative, and that's pretty much all there is to it. Another thing you can do is concavity, right? So that's actually what I ended up saying at first, and I'm glad that the scoring sheet mentioned that. So I wrote the acceleration is negative because the graph is concave down. In other words, the rate of change of the slope is negative, indicating a negative rate of change of the velocity, right? So is negative, I'll put in parentheses, so negative rate of change of velocity, right? I can also put that it's concave down. And what that means is that the second derivative is going to be negative, right? So that has to do with concavity, right? So if you're looking at the rate of change of the slope, well, if my slope is going from positive to 0 to negative, right, and you kind of like trace that out, I have a graph that's downward facing, that's concave down. If my slope was going from negative to 0 to positive, that'd be like a U shape. It'd be concave up, all right? So either explanation works. You can get points for either one. And then it says here for the velocity, so if we evaluate the velocity at t equals 3, I know that the slope is negative, right? So the velocity is negative at t equals 3. So we have t equals 1, the velocity is positive. T equals 3, the velocity is negative, right? You can also mention that velocity is the time derivative of position, right? So that's what it means to be looking at the slope of the line. So yeah, that is pretty much it. Oh, also the acceleration is negative. So the acceleration is negative. And same reasons. All right, I'm just going to put these signs here showing, yeah, same exact reason as before. The rate of change of velocity is negative. All right, so B, the motion of the particle described by this equation, where B and C are constants. Derive an equation for both the velocity v and the acceleration a of the particle as functions of time. Express v and a in terms of b, c, and t as appropriate. All right, well, let's just evaluate it. So for part B, I need to solve for the velocity as a function of time. So now finally we're going to be taking a derivative. So dx over dt. And again, the rule for taking derivatives of a polynomial, right? So again, we have the power rule. All right, so if I take, generally speaking, d over dx of c to the x, all right? What I'm going to do is I'm going to decrease the exponent by 1, and I'm going to divide it by whatever the exponent was. So in other words, the derivative of cx is just c, or I should say cx to the n. It's c over n times x to the n minus 1. That's the rule for the power rule. So you're taking the derivative of a wait, hold on, how do I say this? So if you're taking the derivative of a polynomial, you're just using the power rule for each term of the polynomial. All right, so let's actually evaluate the function. When I took the derivative, I ended up getting v sub t, or v as a function of time, is equal to negative 2t plus b. All right, and then I do the same thing for the acceleration. I know acceleration is dv over dt, right? So I'm going to take the derivative again, and I get negative 2. All right, so derivative of just a constant is 0. All right, and then here I have negative 2t. Derivative of that, we reduce the exponent by 1, divided by what the value of the exponent was, right? So it just ends up as negative 2. All right, so now for part C, this is where it gets a little tricky. So we got to describe the motion of a second particle moving along the x-axis, a term d times t minus 2, where d is positive, constant, and is added to the equation given in part B. Describe how the graph x of t for this second particle is different from the graph given in the first particle in terms of the second particle's position being 0. All right, so for particle 1, okay, I have these two functions. All right, so this is part C. So for particle 1, I'm going to write that x of 1 of t, I'm going to write the function that they have here, right? So for particle 1, I have negative t squared plus bt plus c, okay? Now, if I look at the velocity of particle 1 with respect to time, again, we're going to take the derivative. So negative 2t plus b, and then the derivative of c is just 0, okay? Now, at this point, let's actually plug in some numbers. Or not numbers, let's actually plug in some of the variables, okay? So all you need to do is actually calculate what b, c, and d are. I'll talk about where there's a little bit of a hiccup in the process of figuring out what d is. All right, so we'll get there when we get there. So I know that at t equals 2, the velocity is 0. So, all right, so let's start looking at the graph and start getting some critical information. So at t equals 2, I know the velocity is 0. So I can set the function for the velocity equal to 0 at that time period, right? So negative 2t plus b, all right? And if I do a substitution for t, right, I know t has to equal 2, right? So that's going to equal negative 2 times 2 plus b, right? So that's just b minus 4, right? Is that what I got? Oh, b minus 4 equals 0, therefore b equals 4. Okay. Let's see here. Now, when I solve for... Oh, okay. So that's my function for the velocity. And then here we're going to look at the Oh, we can look at the position as well at t equals 2. All right, so it's almost 2 o'clock in the morning. For the sake of time, what I ended up doing is I tried to solve for all the variables, then I tried to solve for d initially. That's not going to work because you're going to do quadratic equation to solve for the exact values of t, or like coming up with an expression for d. You can't really do it. It's kind of annoying, or at least you can't really do it in a very clean way. You could do it if you calculate it. But here's what I ended up doing, kind of like what made sense to me. So I just, at different values of t, at the end of the day, we're comparing, describe how the graph of x of t, the second particle is different. So at different values of t, I'm looking at x2 of t, right? And then my x2 of t, if I look at that function, right, it's basically x1 of t plus this term, right? The d times t minus 2, right? D times t minus 2. So I'm just adding a little bit there. So at t equals 1, I evaluate the function, and I end up with position negative d. At t equals 2, I end up at position of 1. I'm sorry, yeah, at t equals 3, I end up at position positive d. And then at t equals 4, I ended up at position, what is that? Is that b minus 3 or 1 minus 3? No. It's negative 3 plus 2d. Okay, so at t equals 4, is it positive? Is it negative? Well, it depends. It depends on how large the value for d is, right? So that's basically the value for d is like the initial velocity of the you can think of d as representing kind of like the initial velocity of particle 2. So if particle 2 has a very large initial velocity, okay, it's going to take a while for its position to become negative, right? And that kind of makes sense. You throw something up really, really fast, it's going to take a while for it to come back down. Anyways. So some key features of the graph. We can't know exactly at what time t the velocity or the position is equal to 0. I know the position is negative at t equals 1, and I know the position is positive at t equals 2, right? So at position t equals 1, so at t equals 1, here for the first particle, at t equals 1, the position is 0. At t equals 1 for particle 2, the position is negative d. All right. Yeah, so that's one way in which it's different, right? So at t equals 1, particle 1, actually, I'm just going to write it in terms of the function, all right? So x of 1 equals 0, and x of 2 equals negative d, all right? And because d is a positive constant, we know that the position of particle 2 is going to be negative. At t equals 2, you can just look at the graph. x1 is equal to 1 meter. And when you evaluate it for x2, right, and you plug in the equation, let's see here. Oh, the d term kind of cancels out, right? So d times t minus 2, well, at time t equals 2, right, at like 2 seconds. So I have 2 minus 2, so the d kind of goes away. So it's going to be the same position as x1, okay? So x2 is also equal to 1, all right? And it's saying, so let's go back to the question. In terms of when the second particle's position is 0, justify your answer. Okay, so particle 2 position is 0 at some time in between, or actually, I'm just going to write it as an inequality. So at some time greater than 1 and less than 2, right? Because I know that at time t equals 2, the position is equal to 1, and at time t equals 1, the position is equal to negative d, all right? And I believe that's all they're looking for, all right, if I scroll down, right? Yeah, I am curious as to whether a table would be enough. Let me look at the scoring notes. To earn this point, it's not necessary to use the functional dependence correctly. 1 point is earned for correct justification on why the second particle's position is 0 at time later than t equals 1, and 0 again at time later t equals 3 seconds. Yeah, so I guess that's one thing I didn't necessarily talk about. So at some time later, right, if we look at the function here, right, eventually, I'm trying to think of another way to explain it. So we know the acceleration is negative, right? And the position is positive at, so the position is going to be positive by t equals 2 and t equals 3, okay? And when the second particle's position is 0, justify your answer. All right, so we know that all right, so we know the position of the particle is d at time t equals 3, okay? And as time increases, right, at some point, the particle has to be at x equals 0 again, because this particle is also accelerating with a negative acceleration, right? So eventually the velocity is going to become negative, and if the velocity eventually becomes negative, its position will also eventually become negative. Also, you can kind of see here at t equals 4, the position is negative 3 plus 2d. If d is a small enough value, right, let's say d, yeah, if d were equal to 1, right, then my position would be negative 3 plus 2 times 1, which is just negative 1, right? So at some point in time, right, so at some point in time, I'm just going to put t greater than 3, okay? The position of x2 will equal 0. And it just depends on how large d is, okay? And there is a way you could write an expression for d. I think that was what I was first trying to do, but that gets really messy, and you have to use quadratic equation. And I guess like the kind of like, you know, why am I bothering to tell you this? If you ever run it down like the wrong road when you're working on an FRQ, these should not be taking like it should not be taking terribly long, right? There's not much time to actually work through the FRQs. Most of them need to be done within like 25-ish minutes, 20 to 25 minutes. The lab ones may take more than that, right? You can say like roughly like 30 minutes. But at the end of the day, I think you get, what, hour and a half? Yeah, so you get an hour and a half to do your FRQs. And I think you have 4 FRQs on the test. Not the test on Friday. I'm just saying for like the AP exam. So, yeah. And that's roughly how long I spent kind of explaining all this. I just wanted to be as thorough as possible with the explanations. But this has gone on for long enough. If you have any questions on any of the FRQs, just stop by tomorrow after school, or I guess today after school. And also for the multiple choice, if you have questions on the multiple choice. I don't have time to go over the multiple choice, but if you want to have a deeper explanation, or if you were confused, like when you're checking your answers, like if you weren't sure, if you didn't know why the correct answer was what it was, you can ask me and I'll help you out with that. All right, well, anyways, good luck, and hopefully